Yes, now I would like to invite our next keynote speaker, Henrik Madsen from DTU. I had the pleasure of working with Henrik for quite some years now, and he had always been a large inspiration for me. I never told him that before, but he have inspired me a lot. And yes, it's recorded, you know, you can show it to the rest of the gang when we come home. And lately we worked on a project where Henrik was the PI, Flexible Energy Denmark, and together with some of the other universities in Denmark. And it was really interesting to try to explore how flexibility might be the next step forward in balancing our energy systems and in that way try to make the green transition happening. And this is also, I think, some of the work or related to that you are going to talk about today. So I look forward to the keynote speak. Thank you.
Thanks a lot, Bo, and thanks for the collaboration we had, Grace and Bo, during this project, and also collaboration with some of your PhDs and postdocs. Yeah, so I think in my presentation here, there will be 2 or 3 main messages. One of the messages is, one of the learnings is how to connect energy markets, conventional energy markets, to the physics, and take into account the physics in the way you operate the markets. And that's a so-called flexibility function, which I will introduce. And then I will also argue that we would need, in order to have models, we need a hierarchy of models. We need a spatial temporal hierarchies of models. We need the models to be coherent on different temporal and spatial scales. So that's something we are zooming in on also, and will also be a part of the message here. So just to setting the scene, we are moving towards a system where which will be weather driven. So basically in Denmark we will have wind and solar. We don't really have hydropower in Denmark because it's a flat country. So every energy will be produced by wind and solar. And in the old time, we developed software, IT solutions, and so on for the power plants, the central power plants, and so on. But they will be gone, and we will only have the wind and solar. And that means that in order to balance the power system, we need the intelligence on the demand side. So we need to, and that calls for massive use of AI, IoT solutions, and communications, and so on. So some of the challenges we are faced with is that I think I'm coming from applied mathematics and computer science, and I think when we talk with grid operators, so they tend to focus very much on just putting more cables in the ground or having batteries. But I think they tend to overlook the potentials of flexibility. These slides are some of the slides we had when we started the Flexibility Energy Denmark project. So it has been realized also during quite some years, and this is a report which we drafted for the Department of Energy in 2016. I was one of the co-authors of this report, where we showed that in order to unlock the needed flexibility, we need to focus on energy systems integration or sector coupling, and we need actually also to consider data. For instance, data is the glue which can make this work. And another thing which was also already mentioned in this report, we need models which are coherent between customer level, city level, and a regional level, and all these spatial zoom levels. The models need to be coherent. So one of the challenges I think we have is that people think, or many people from the power industry, energy industry, thinks that we can bid in on the markets. Everyone can bid in on the markets. But we have done a lot of test experiments. For instance, together with our TSO and EnergyInformatics, we did a series of workshops and tests with wastewater treatment plants. And wastewater treatment plants can offer a lot of flexibility. because they have overcapacity and so on. But they will never be able to bid the flexibility into a market, because their main concern is to avoid overflow in the city. There might come up, if they come up a thunderstorm in 6 hours, then they don't care about prices. They only care about avoiding the overflow in the city and things like that. So prices are the market position is not on the top level, but of course most of the time they can offer a lot of flexibility. And also, I think on a street level, if you are looking into the distribution net operators, the DSO level, along a feeder, there might be 40 houses and a supermarket. And this can never form a market. The liquidity, the size of it is simply too small. And also ordinary people, they have difficulties in bidding into the market. So, thanks a lot, Paul. So, and I think also people, if the flexibility really depends on the price. So the way of doing bidding, we're just saying that I can be that ordinary markets. You have this merit order bidding. You have the cheapest and so on, and then you have this crossing. And this is, from a mathematical point of view, a static and a deterministic way of doing it. But if a supermarket on this feeder has been flexible for this half an hour, then it cannot be flexible the next half an hour probably, because then the milk will be too warm. So we need to go away from a static thinking to a dynamic thinking. And also when you zoom in on a street level, the stochasticity from the individual households, and also now with more PV production and things like that, we need to go away from this merit order bidding, which is deterministic, to a stochastic setting. And we need also, when we consider sector coupling, we will also be faced with some nonlinearities. We cannot simply stack the bits. So what we believe in is that we simply need a rather simple system where the flexibility functions are used to describe the stochasticity and dynamics and the flexibility on any spatial and temporal levels. So be aware of that we can have different zoom levels. We can talk about a DSO, we can talk about a single house, we can talk about a city. And for all these zoom levels or aggregation levels, we can have their flexibility function. And then we simply broadcast a price, which we send to this area. And this price is deformed, so it solves all the operational problems in the grid, and I will come back to that. I also think when we talk about the normal bidding, of course, flexibility depends really on the price. If the price gets really high in Denmark now, I will get a warning on my phone and I'll call my wife, turn off everything. So if it costs 1 million, because we'll be ruined in less than 10 seconds then. So it's really the causality, and I'm coming from mathematics, the causality comes from price to load, and the other is simply ridiculous to do this in another way. So now I'll zoom in on, first I will mention something about some reports, also some results from the Flexible Energy Denmark project and the Cities project, which was a similar sort of project, but also a report which came out end of last year about the benefits of demand-side flexibility. What we have learned is that we can save up to 80% of today's predicted investment needs until 2030 by effectively activating demand-side flexibility. And that's a lot. Of course, it's a lot. There's a span here, but even with a lower level, it's a lot of money. The balancing cost today, with the way they operate with the market operators, that's very expensive. And in most cases, we don't need them. We can replace these expensive operators. In Denmark, it's called Energy Denmark, Danske Commodities, and so on, with simple computers and control theory. And all over, and again, these are European numbers, they have estimated that we can save between 43 and 66% of the balancing cost. Again, these are huge numbers, a lot of billion euros. And also today, we curtail wind, Very often we stop the wind turbines when we have a lot of wind because we are not flexible enough. We don't have enough demand side flexibility. Similarly for the solar, there are cutoff in how much we can put into the net. And so we lose a lot of green power, and then later on we use black power instead. So why we should definitely just activate demand side flexibility. Again, the estimate is we can save quite a lot. And based on a lot of experiments, we can see the end user can save on top of that between 10 and 80% of their bill by being flexible. So we have been working with this competitive bidding using flexibility functions and real-time pricing since 2008. So one of my PhD students, Marco Sugnu, suggested that we could take into account by the dynamics simply by using control theory. Instead of having using ordinary optimization, what they do today in market clearing, we could use control theory, because then you take dynamics into account. And the uncertainty, the stochasticity, can be taken into account simply by considering stochastic control theory, because then you take into account both dynamics and stochasticity. So, so that was basically the start of this with a control theoretical approach and hierarchy of controllers. We need another element here. We need models. We need models on all levels. And basically what we are looking into are what we call data-driven digital twins or gray box models. So typically they are simplified models for instance, a building. It could be a model with 3 or 4 stages, or 2 stages, 2 RC coupled models, or it could be, so they are simplified models, but the models take into account both the dynamics, of course, but also the uncertainties. So the models we are using are stochastic differential equations typically, which implies that it's okay then to reduce the number of differential equations and then compensate by that by introducing what we call the diffusion term in the stochastic differential equation. Then we describe everything in every dynamics and stochastics just with a few parameters. So, and another thing which is important is that we need to be able to do this in real time. And the first model we got for wastewater, we're doing a lot on wastewater, smart wastewater handling. The first model we got some 15 years ago was a model with 43 coupled nonlinear differential equations. And it took us 1.5 hours to calculate what will happen in 5 minutes. And that's, yeah, maybe we could have been smarter, I guess, but it was not really useful. So we throw away these deterministic differential equations and replaced it with gray box models and stochastic differential equations. I think today we have 6 coupled nonlinear stochastic differential equations. And another thing which is very important is that the fact that we are taken into, and the fact that we describe the noise in the model means that we are able to assimilate information from sensors and data into the model parameters. That's not possible with a full-blown digital twin. So, so there are several aspects here which are very important. But the models in general are simplified. So, and then another thing which I also mentioned in my introduction, which is important, is temporal and spatial coherency. So the models should be coherent on any temporal scales. We should be able to zoom in and out, consider appliance or a city or whatever, and go back and forth. And the models should just be coherent. They should be linked together. So, so yesterday we saw a presentation by Dr. Wesley about, a very good presentation about forecasting of solar radiance, I think, where he showed on the 5-minute horizon, the best was a Kalman filter approach. On a 1-hour approach, I forgot what it was. Yeah, you were here. But it was, there were different models, and that's fine. And but using coherencies, we can couple the different models so they can help each other, and we can zoom in and out in space and time. So the temporal and the spatial scale is just important, and of course the sector coupling. We have put that into what we call the smart energy operating system. So that's a framework of models arranged in spatial temporal hierarchies which on the lower level here describes the dynamics of the wastewater treatment plants or the buildings and so on by these simplified models, gray box models or data-driven digital twins. On the higher level, we still believe in markets, because if you zoom out and consider the Nordic area, Scandinavia, whole of Brazil or whatever, then the dynamics and day ahead and so on, then the dynamics at stochasticity is, we don't need to take that into account. But we have a price level which reflects the water, the amount of water, for instance, in Norwegian hydropower. So we need this conventional market when we zoom out in space and time. But when we zoom in, we need to go away from static and deterministic thinking to dynamic and to stochastic thinking. And the key element here is these flexibility functions, which are used to link market to the physics. And this flexibility function is now going to be an international standard for operating energy, smart energy systems. So it's going to be one of these minimum interoperability mechanisms, which is defined by United Nations and so on. And we have just a hierarchy of controllers which takes into account the different problems in the network. And I will come back to that, how we do that. So, yeah, sorry for a little bit of math here, but these are the two lower levels in the smart energy operating system, or just some examples on how it could look like. And here I might have have a building in mind, because I'm using a linear differential equation. That's typically a model which can be useful for buildings. Here a building owner will probably try to lower the cost. So he's using typically a controller which could be an economic MPC type of controller, and that's look like this. So he responds to the price, and on the higher level here, the DSO or whatever we have here, he would probably try to do some peak shaving or voltage control or whatever. And so he might have some reference load which he would like to follow or be below or something, or reference voltage, so it could be many different things. So he has such a, this is called a reference-based of stochastic controller, and the model here is a model which simply links the price to, for instance, the load. And that is, since we have people in the loop here, it's not a white box model, of course, because yeah, it's what people are doing is unpredictable, right? So we need AI, we need rather black box oriented models, but we have these models which links the price to the load, and this is the flexibility function. So that's, and this can be the flexibility function for all the buildings on this feeder here. So the price is sent to all the buildings to get the response to keep, for instance, the temperature of the transformer station below some level or whatever. So that's just some examples on how it looks like. And maybe now we just take a very simple example on peak shaving, which is very easy for you to understand. So if we have on this feeder 20 houses, and that's the real data, then we can see that here when the prices goes up, the load went down, and when the price went down, the load went up. So what we need now is a relationship between the price and the load. And these are just two time series. And I, some years ago, I wrote a book in time series analysis, and there are some exercises. And this is probably exercise number 2 or 3 in the book, how to find a dynamic model between price and load. So this could be an Armax type of model, whatever, or Box-Jenkins type, but yeah. And yeah, in this case, for this data, the step response function. So if we have a step increase in price, then the load went down to about up to 15% for up to 5 hours. This was a project with the US. In Denmark, the buildings are better insulated and more heavy. So it's not 5 hours, it's more 12 hours on average or something. And it's also a little bit more, going a little bit more down. So this is the first proposal for the flexibility function. This is simply a step response function in time series analysis. If you have studied time series analysis, you will have heard about impulse and step response function and things like that. And this is simply how it could look like in a general picture. So that's a flexibility function with different characteristics, and that's this fundamental tool for linking the market to the physics. So if you have estimated the model between the price and the load, which I just explained before, could be an Armax model, simple model, exercise number 2 in my course, then you have this model. And if you have this model, then you can also derive a controller. So you send the price which can control the load. We also have a course on stochastic control theory, and this is maybe exercise number 3 or whatever. In this, if you have an Armax model, how then to design the controller so you control the load. So basically, rather basic stuff, I would say. So this is the total setting for controlling the peak load, and this is what we achieved in that case. So we removed the morning peak and the afternoon peak. And of course, this could be used for many other things, because this model could be between price and load. It could be between price and voltage, or price of the temperature of the transformer station, or price or frequency in the bigger area, or yeah, whatever. It could also be, instead of prices, of course, if we are using real-time prices, we are minimizing the cost so then it's cost efficient. But instead, we could also use real-time CO2. Then the buildings is operated so it's emission efficient. We are minimizing the carbon footprint of the operations. So that's also a possibility. Or we can just minimize, it can just be energy efficient. That's a constant penalty. So, and we can have a combination of this. And we can have a combination, and I'll come back to how we do voltage control and so on. With this setup, again, we have the flexibility function and the controller. And with this penalty function can use a combination of this cost, emission, energy efficiency, whatever we like to study. In the case with flexible in Denmark with Bo and Grace, some houses where we had a main focus on CO2 efficiency or emission efficiency. Some houses were on the cost. But then we can also use the controllers which then control the voltage and so on. So we were already described how it looks like. So we just have a quadratic controller and then a linear controller, the economic MPC for all the houses, and then we can control we can generate the price and control the load in both electricity, and we could also do in the district heating grid. We'll come back to that. If we instead of having the load here, if we then just introduce the voltage, then we control the voltage. And in district heating, it's not the voltage, of course. It's the temperature, the pressure difference. So in district heating, we need to be able to show where we have a pressure difference along the district heating network. But it's the same, the mathematics is the same. We can also control the frequency for the TSO. So the conventional setting is this market bidding here with price bidding and so on. And then what happens on the DSO level is really more or less a black box, as we also heard yesterday. It's difficult to see. There are now, we saw some very interesting discussions yesterday where we are getting a little bit insight in what happens. But the way that it's operated today is really like more or less like a black box. But instead, we suggest to have this control problem, solving frequency, voltage, balancing, and so on. We can also do the balancing, and we can have an aggregator which bids into the high-level markets and save extra money. So each control problem here is a part of the hierarchy, and they create a part of the price, and that the final price which enters the house is a combination of all these prices. So that's why I say we are having a hierarchy of controllers. We can even, the good thing is also that, the one problem with existing market things is it's difficult to bid in the flexibility on different type of markets. Today in power systems, you have one market for the ramping, one market for the TSO for keeping the frequency, another market. So which market to bid into? That's ridiculous. But with this concept, we can just offer the flexibility for whoever wants the flexibility or needs the flexibility. Another thing is we need to do sector coupling, as I said initially. And in Denmark, we have a lot of district heating. I think around 70%, correct me if I'm wrong, 60-70% of the houses are heated by district heating. And this is just an example where we have 5 houses all having district heating, where we might do peak shaving, like I did for this electricity case before, and we control the pressure difference, like I also showed before. And then 2 of these houses has also installed a heat pump. So because we would like to reduce the number of times the wind turbines are stopped. So the hierarchy of controllers can easily be extended just to have this setting with sector coupling. So it's a trivial thing to add on another energy supplier. So we can automatically switch between district heating and electricity. Let me zoom a little bit in on here towards the end on the importance of spatial and temporal hierarchies, which is also behind what I just showed with the models. Now I'll zoom a little bit in on forecasting. And this is something we have done for our TSO, EnergyNet. And this, the data I'll show is from what we call DK1, the western part of Denmark. So this is a tiny area compared to Brazil. So Brazil will be the entire room, I guess, or more. But even though we, so when we do the wind power forecasting, we can make a model for a single wind turbine. We can also make a model for a wind farm, or for the substations which might connect different wind farms, or maybe the different regions here which EnergyNet operates due to the layout of the high voltage grid. And we could also be the entire DK1 area. So the models we have developed, we have different models for the wind farms compared to the upper level. But we ensure using this, the spatial hierarchies, that the models are coherent. They talk to each other. So they learn from each other. So this is typically the model building. You'll say maybe you do a bottom up. You add models for this, then you add this and add this and this. This is a bottom up approach. Or you can use a top down approach. But our approach is a combination. So it takes the best of both worlds. So it's a combination of bottom up and top down. So I will be happy to send you some papers. We are working on the mathematics right now, and there will be a paper out in 3 or 4 months describing the mathematics in detail. And also, if you would like to see some equations, we can take that in a break. But in this case, for instance, for DK1, we improved the wind power forecasting up to 20% using spatial hierarchies. And we can also use temporal hierarchies. So we can, for instance, like you presented yesterday, we can combine your Kalman-Filter model with I forgot the model, the Armax model, and so on. So they can be linked together and learn from each other. We are doing wind power forecasting worldwide, also in Brazil. And I can actually see this map is a bit outdated because I know we do it in Chile now. They visited us 3 weeks ago. So but we are forecasting up to around 25 to 30% of world's entire wind power production. We also do it for solar, wind, and load. Solar, it's a bit about 15%. So at the end here, I would like to mention that Bo, Grace, and I, we have been involved quite a lot in an IEA Annex 81 on grid integrated smart buildings. And I see some people or some of our friends from Hong Kong also. We have some collaborations, for instance, on smart buildings in Hong Kong, with Hong Kong, and which also participated in the Annex 81 meeting. We also have, there's also another Annex 82, which is zooming in on the flexibility function and how it's used for operating buildings and so on. But there is a new project concept proposal, which is now actually approved by IEA. So it will take off. And it's led by Cesaro in Australia, Stephen White, which is also the leader of IEA Annex 81. And Rong Ling, which is leading of Annex 82, she will, together with me, be co-operating agent or whatever it's called. So, and the idea is to couple the annex on data-driven smart buildings, Annex 81, with energy flexible buildings towards the low-carbon energy system, that's Annex 82, in one new IE annex, which is grid integrated smart buildings. So I have suggested what we call the Smart Energy OS, Smart Energy Operating System Framework, which is a hierarchy, spatial temporal hierarchies of models using stochastic description of what's going on and dynamical descriptions, of course. And I have tried to argue that we can save a lot. Of course, you should probably consult our homepages to see the actual cases. Some cases you only save 10%, sometimes. For instance, for data centers, we can save up to 80%, for instance. For wastewater, we can save up to 50%. The Smart Energy OS controllers with the hierarchy can focus on peak shaving, voltage control, frequency control, whatever. It could also focus on energy efficiency or emission efficiency and so on. And the flexibility function is the key element to this. That's a building block. Yeah, I think that's it. I forgot my bio, but yeah, I'm an old professor in mathematical statistics, and yeah. Thank you.
Good. Thank you, Henrik. Thank you. I enjoyed your speak a lot, and I just have one fast question for you. So, if you should not call your wife to turn off everything that was running, right? So I was thinking, have you tried to experiment with some integration with maybe some price-based control on the demand side, or some budget-based control to limit? I mean, run a budget on how much people can afford to pay for the electricity, or to fully automate the whole integration.
Yeah, basically we are doing that in a lot of case studies. Yeah. And if we zoom in on buildings, we also have human in the loop feedback. So we have an app where people can talk about the indoor comfort and say whether they like it or not. So we have both the physical sensors, the CO2 sensors, and temperature sensors in the room, but we also have the feedback. So we combine this feedback from the physical sensors with feedback from the human, from the apps, which evaluates the indoor temperature.
I think you had a good case with some swimming pools, right? In summer houses for saving money also.
Yeah, we save money basically in all cases. For what we did with the summer houses in Denmark, we have a lot of wind, and as I said, we are often turning off the wind turbines because we don't know how to use it. So one thing we did in this Flexible in the Denmark project is we used summer houses with swimming pool simply to store the excess heat. So we simply overheat the swimming pool a bit, not so people are boiled, but up to maximum 32 degrees, and normally it's around 25 to 26 degrees. And then due to the large thermal mass, if we raise the temperature of 3 or 4 degrees, we can turn off heating for the next couple of days or something like that. So that gives a lot of flexibility. It saves a lot. I think it's up to 30% or something for the summer house, as far as I recall.
Quite a lot.
Quite a lot, yeah.
Good. Okay. Thank you, Henrik.
You're welcome.